A 2-decade journey in laser trapping, a micro step toward clean energy. Nearly 20 years ago, when we began this journey, clean energy wasn't on our minds. We were simply curious about blood. Specifically, we were fascinated by the elasticity of human red blood cells. Their flexibility is essential, and we wanted to know. To explore that, we turned to laser trapping. Our initial goal was modest: apply force, observe deformation, and learn about the mechanics of life. But science has its own rhythm. To stretch the cells more, we needed more power. And as we increased the laser intensity, we noticed something unexpected. The cells began to twitch, move erratically, and then, suddenly, they would eject from the trap. After countless experiments, we discovered the cause: ionization. The cells were breaking down under the laser's intensity, accumulating charge until electrostatic forces launched them out of the trap. We developed a theory to estimate the radiation dose that triggers ionization, first applying it to red blood cells, then to cancer cells. The cancer cells took longer, revealing that our technique needed refinement. But the observation sparked a new question. What if, instead of ionizing a single cell, we could ionize an entire microvolume of blood? What if we could create plasma, a dense cloud of charged particles, and expose it to the laser's oscillating field? Could we generate electromagnetic radiation? Could blood shine? We tested the idea. For 2 hours, we exposed whole blood to intense infrared laser trapping. And yes, it radiated visible light. The blood glowed. That was a breakthrough. But 2 hours wasn't practical. We needed speed, so we turned to magnetism. When micromagnets interact with a laser trap, something extraordinary happens: a microscopic dark bubble forms. We first observed this during experiments with BT20 cancer cells mixed with magnetic beads. The bubble rapidly expanded, drawing in surrounding matter without letting anything penetrate. And then, at a critical moment, the bubble exploded. It incinerated everything nearby, instantly forming plasma. We had found a path to fast plasma formation and rapid radiation. That opened a new door. If we can create plasma in microvolumes, what happens when we scale it up? Can we create a radiation? In our lab, using just 400 microliters of bovine and horse blood, we have observed a very intense radiation that lights up the lab room. Could we transform biological waste into power? Could this revolutionize the meat industry, not for food, but as a source of clean energy? And still, we kept asking, can inorganic materials do the same? This spring, we explored the interaction of micron-sized silicon, polystyrene, magnets, and yes, animal blood. The results? Light, plasma, radiation. What began with a question about red blood cells has grown into a micro step towards something greater. A new way to see waste. A new way to think about energy. A new way to light the future.